Hello everyone. For this last video in this chapter, I'm going to show you two tricks to solve square system of linear equation. One trick will be using the inverse, which is probably my least favorite tricks, except if you have square systems that are given by a coefficient matrix that is 2 by 2, and the one that I will force you to fall in love with, Kramer's rule, that uses determinants to compute solutions of square system. So two different tricks in two different sections, but they're fairly simple. So I'm going to combine this into one nice, clean video. So the first trick in section 3.6 is how to use a square system using the inverse. So first of all, what is a square system? So a square system is simply a system of linear equation where you have n equations of n variable. In other words, in a square system, the coefficient matrix A is always a square matrix n by n. And guess what? In this class, our square systems are going to be either 2 by 2 or 3 by 3, talking about the coefficient matrix. And the big first theorem is that if you have a square system, the square system has a unique solution if the determinant of that coefficient matrix is not zero. And the proof really relies in the fact that we have an inverse, so we can get rid, like when we have a matrix where the determinant is not zero, we have an inverse and we can use it to get rid of it. So if you have a system of linear equation, we will see together that you can write your system of linear equation in matrix form as coefficient matrix times x equal to b. And the idea is that if A is such that the determinant is not zero, we know there's an inverse. So you take your equation and you multiply both sides by the inverse. What will happen when you do that? Well, when the inverse is going to meet A, because the inverse is a matrix such that when you multiply by A, you get 1, or the identity matrix. And because the identity matrix times anything will just give you that anything back, this means that when you look on the right side, A inverse times the augmented part is actually that unique solution. And if this proof feels fishy, and I'm never going to ask you to do a proof, you actually know this already. For example, if I say solve 5x equal to 2, what you would say is, oh, let's just divide both sides by 5. But if I want to keep the spirit of the inverse, one way to overkill this computation is to say, well, I know 5 is a 1 by 1 matrix where the determinant is not 0. I can multiply both sides by 1/5. And what happens when I multiply both sides on 1/5 by 1/5? Well, 1/5 times 5 is 1, and 1 times x is x, and 1/5 times 2, or the inverse of 5 times 2, gives you your unique solution. It's the exact same idea here. It's just we're using fancy terminology and notation, but it's the exact same thing. The unique solution is the inverse of A times B. It's like I'm dividing by A on both sides. So how do you solve a square system? The first method, using the inverse. Well, you first write your system in matrix form just to be able to read clearly what is A and what is B. Then you compute the inverse. If it's a 2 by 2, we have a nice formula. If it's 3 by 3, it's a Gauss-Jordan question. And then the unique solution is obtained by doing matrix multiplication, where you multiply the inverse by the column matrix or the vector B. So let's just do examples. I'll do a 2 by 2 and a 3 by 3. I will not, for the 3 by 3, do the detailed computations, but of course you do it. Those are perfect practice questions to master computing the inverse. And of course, again, matrix multiplication. So solve the following. So my first example, a 2 by 2, solve the following square system using the inverse of the coefficient matrix. And again, I think for 2 by 2, this is very, very efficient, and you'll see why in a moment. So first and foremost, I write my system in matrix form so I can really see the coefficient matrix of that question is 2, 4, 3 minus 5. The x vector, the vector of variables. So here, this is A. This is my vector of variable, and the augmented part is B. The idea here with this notation is that if I was going to multiply xy by the matrix A, you would get 2 times x plus 4 times y equal to 2. And then on the second row, you'll get 3 times x plus minus 5 times y is equal to minus 19. So you get the exact same thing. So this is just two different notation for the exact same thing. But then in matrix form, I can first check if A is invertible by computing the determinant of A. Again, how do you compute the determinant? It's time to draw some fishes. Okay, so here we go. Fishy, fishy, fishy. Oh, I'm going to have to use a different color here. So let's draw a fish. So here, 2 times minus 5 minus 4 times 3. So I compute my determinant. So you get 2 times minus 5, following my fish, always from the top left corner. So 2 times 5, then through them out, minus 4 times 3. If you do the computation, you get minus 10 minus 12, which is minus 22. This is not 0. There is an inverse. And how do you get the inverse? Remember, for a 2 by 2, we have a nice direct formula, shortcut. So it's 1 over the determinant. So this is my first example in my notes where the determinant is not just 1. So we're going to get some action here. And then remember what I do with the 2 and the minus 5. They just swap places. So the minus 5 goes to the top left and the 2 goes to the bottom right. And I change the sign of the other 2. They're not moving. So you get minus 4 and minus 3. And my advice for these questions, leave the inverse like this. If you enter the 1 over minus 22, you're going to create fractions, and you have to do a matrix multiplication here, and you want to avoid doing fraction arithmetics. So my advice, because I'm so nice, don't bring the 1 over minus 22. Keep it like this. So now you get your final answer. So the solution, xy, is going to be the inverse, so 1 over minus 22, times minus 5, so the inverse, so 1 over minus 22, minus 5, minus 4, minus 3, 2, and then I multiplied by the augmented part. So this is a matrix multiplication question. So perfect for me on a test. I want to test you on matrix multiplication. I can just ask you to solve a square system using the inverse. So there's an inverse computation with Gauss-Jordan, and then there's a matrix multiplication. So here we go. So if you do the math here, so again, I'm keeping the 1 over minus 22 for now outside. And now if you do your computation, you're going to get minus 5 times 2 plus minus 4 times minus 19. This is going to give you 66. And then downstairs, you're going to get minus 3 times 2 plus 2 times minus 19. And this is going to give you minus 4. And then once you do your actual computations, so now this is when I'm going to enter that minus 22. But see how clean these things are. 66 over minus 22, that's minus 3. And minus 44 divided by minus 22, that's a 2. And that's my unique solution. And of course, you can check that this unique solution is the right one, minus, like by plugging it into the system. So if you take minus 3 times 2 plus 2 times 4, you can double check that this gives you a nice clean 2. And then minus 3 times 3 plus 2 times minus 5 will give you a nice minus 19. So we know that this minus 3, 2 is the unique pair, the unique solution for this square system. So again, write your matrix, sorry, write your system of your equation in matrix form, label A, label X, label B. Check if A is invertible by computing the determinant. For 2 by 2, you use the formula and the trick. And then the inverse times B, nice matrix multiplication, gives you the unique solution. All right, let's do one more example. I'm not going to go through the computations. I just want to show you how to compute the solution once you have the inverse. But the next example, you have all the detailed computations to get to the inverse. This is, again, perfect practice to master Gauss-Jordan, so getting that inverse. So I have now, for my second example here, a 3 by 3 system. So the first thing I do is I write that system in matrix form. So the coefficient matrix of that system, a nice square matrix, 3, 5, minus 2, 1, 0, 4, 0, minus 1, 3. That's my A. That's my vector. My vector full of variables, that's my X matrix. And then that's my B, my augmented part, 4, minus 1, 7. Again, here you should feel that if you were to multiply A by X, you would reconstruct this 3x plus 5y minus 2z, for example, on the first row, and etc. You're going to be rebuilding the system. It's the exact same thing, but it's just in matrix form. Now, if you do compute the inverse, so here I'm not going to do it, but if you construct the super augmented matrix, and please do it, you have all the details. You cannot say that you don't have enough examples. If you take A augmented by I and you apply Gauss-Jordan, please verify that the whole reduced echelon form of that matrix is I3, and the augmented part is minus 3, 13, 20, minus 20, 3 minus 9, 14, and 1 minus 3, 5. And that's the inverse of that matrix. And again, it's super fun. If you multiply your matrix A with that freshly computed inverse, you can verify that this gives you a clean identity I3. Or if you take that freshly computed inverse times A, you also get the identity matrix I3. Again, super good practice for matrix multiplication. This is a perfect way to spend a Friday night. Like, hey, I have nothing else to do. I've been watching TikToks all day. Why is my life going nowhere when you could be doing Gauss-Jordan to compute inverse of 3 by 3 matrices and verify that this inverse is indeed the inverse, because when you multiply those two matrices together, you get the identity matrix. And now we get this brand new thing where we can get the unique solution of our square system by computing the product between A inverse with B. So if you do your matrix multiplication, so this is a nice exercise for matrix multiplication again. So if you take the B matrix, so the vector or the column matrix, and you compute minus 4 times 4, 13 times minus 9 plus minus 20 times 7, verify that you get minus 273. And then on the second column, 3 times 4 plus minus 9 times 9 plus 14 times 7, verify that you get 191. And then finally, 1 times minus 2, 1 times 4, sorry, wait, 1 times 4 plus minus 3 times minus 9 plus 5 times 7, verify that you get 66, and that's your unique solution. And I think here, you can find, of course, a solution just using Gauss-Jordan. But if you have the inverse, might as well use it. And typically on an evaluation, I typically just ask you for the inverse first, and then what a coincidence. Part B of that question is, hey, we have a square system, and it turns out that the coefficient matrix is the one where you just freshly computed the inverse, and then I'm asking you for the solution. Well, the solution is A inverse times B. So one quick matrix multiplication, and you're done. Okay, so I think I will actually end this video there. Okay, so I will, even if I announced I was going to do the two tricks, I think I'll split that one very quickly so that you can maybe go and enjoy this new fact that the unique solution is A inverse times B when you have a square system where A is such that there's an inverse. Anyway, so for that video, okay, so sorry for the pause announcement. I'm a bad teacher, I know. But anyways, for 3.6, solving a square system with the inverse, that's it. That's all. Bye-bye,